Okay, so let's say this town has 1,000 people and it's going to grow. And so by one scenario, it'll grow by 100 people per year. Okay, so you hopefully will recognize that that means that it's a linear function, right? Let's say another scenario is that it grows by 10% every year. Now, if you think about it, this perhaps is a little bit more realistic physically, right? If you're adding 100 people, it means that perhaps 100 people are moving into the area and they're unaware of the population of this town. But by growing 10% a year, that means that perhaps there's some sort of internal process that's making it grow. You know, like think about birth rates. Now, birth rates, heaven forbid, aren't 10% per year, but you know, if a birth rate is perhaps, you know, one child per every 100 couples or something like that, then you would expect a whole lot more births to happen when the population is large than when the population is small. So things that are proportional now will grow a little bit differently than things that are linear. So if we look at the equations behind this linear function, let's say y is the population, the subscript refers to the time. So the initial population, we add 100 per year and we get the population at the end of year 1. And so we can, you know, keep on going. We take the y2, which is the population at the end of year 2. We take the population of year 1 and add 100. And so if we go back to our initial population, make a general formula, we can say the population at the nth year, let's say the 10th year, is going to be the initial population plus 10 times the 100 people it grows every year. Okay, so at the, and I'll have a numeric example on the next slide, but you know, this is just basically a linear formula where this is the initial, this is like your y-intercept, and then this is, you know, your value of the number of years times the rate of change, which is the slope in the case of a line. And so there's our general formula for the first scenario. Second scenario, we get similar formulas, but they work a little different. So what we're going to do is we're going to take a 1, which means we're going to keep the initial population and add 10% to it and multiply it by that initial population to get the population at year 1. Okay, so in our case, if we have 1,000 people, we multiply that by 1.1 and we get 1,100, which would be the population at the end of the first year. So if we extend that to be multiple years, we say, okay, y1, at the end of the first year, we multiply that by 1.1, and we get the population at the second year. We can, of course, make the substitution from the initial population. We're going to take 1.1 squared times the initial population to get the population of the second year. And so the general formula is going to look like this, where now the n, which is our variable, the independent variable in this equation, is now an exponent rather than, you know, a coefficient. And so at the 20th year, what we're going to expect is take 1.1 to the 20th power times our initial population, which was 1,000. Okay, so this is the way exponential functions arise, is that we just get this essentially compounding every year, and that's the way it works financially. When you have money in the bank, you know, you get the interest on the interest that you've earned the year before, and so it grows exponentially. All right, so let's look at what this means from a number standpoint. So scenario A was it grows by 100 every year. And so at the end of 6 years, you have n times 100. 6 times 100 is 600, plus the initial 1,000, and we get 1,600. All right, scenario B. So the first year, it grows by 10%. 10% of 1,000 is 100, so you get 1,100 at the end of the first year. Now, on the second year, it's going to be 10% bigger than 1,100. So 1,100, 10% of that is 110. And so it's going to be not 1,200, but 1,210, because that initial addition of the 100 in the population now has contributed 10 to the next one. And this is just going to go on. And so we take 10% or 1.1 times each of the previous values, and rounding off, of course, I'm going to be ending up with some fractions in here. I just rounded off to the nearest whole number because we're talking about a population. This is what we would expect. Now that's not too different, 1,600 from 1771, but if you look at what happens at 20 years, you see the population is over double with exponential growth than with linear growth. In fact, you hear that expression quite a bit. Oh, things increased exponentially. You know, that has a very specific mathematical meaning that means that the growth accelerates as time goes on, that it isn't a constant growth. Usually when people say it grows exponentially, it means that it grows a lot. Well, you can have modest growth exponentially with a small factor. So it doesn't necessarily reflect the size, but it's more the characteristic of the growth. Okay, so if we look at a graph, so in this case exponential growth, you can't read the scale on the side, but all of this is just what I had in the table before. Linear growth is a line, exponential growth is a curve. And it looks a little bit like a parabola, but it's not a parabola. In some cases you can model it as a parabola, but a parabola, remember, is symmetric. It will increase as you go to negative numbers. Exponential, if I were to continue that curve on the negative side, it would get progressively smaller and smaller and smaller and closer to zero. Okay, so that's what the graphs look like. Okay, so let's talk about the exponential function a little bit more algebraically. All right, so this is the form generally. And so what we have is we have a coefficient. We have what's called the base. And then the exponent is the independent variable. Okay, so we can refer to x as either the variable or the exponent. The base b is generally, well, it is in exponential functions a constant, and a is a constant. So we have two constants. Remember, just like with a power function, we had ax squared for a parabola. A and the 2 are constant. Here, it's the a and b that are constant. The exponent is what's the variable. Now, if we're dealing with growth, oftentimes the variable is time. And so that exponent then is the amount of time. And then you talk about b as being the growth or decay factor, and a turns out to be the initial amount. Because remember, if t equals 0, then b to the 0 is going to be 1, and so a is that initial amount. And so it's very easy to read an equation that's describing exponential growth, because you see what the coefficient is. It's the amount that you start with. And then just like we added the 10% to the 1 plus r is the percentage growth or decay rate. Now if r is negative, it's going to be decay, and that's what happens with radioactive decay. But in our case, with that 10% growth, the r was 10%, so the base turned out to be 1.1. Okay, so it was 1 plus that.
With the alpha.
Yes.
Are we always going to be using like proportions for that, so like 1 to like 0.1?
We're going to use all sorts of numbers. You'll have some fractions in there. You'll have whole numbers. You know,
Okay.
all that. The reason why I'm showing this is because this is where you're going to see it most commonly. Mm-hmm. And my understanding is most of you are chem and bio majors, and so exponential growth and something that you're going to learn about in Math 28, logistical growth, is very, very common way to describe growth. And in that case, when we're dealing with growth of biological systems, you know, you usually end up with small numbers like 1.1 or 1.05 or, you know, stuff like that. Okay, so let's look at an example more in the financial world. So let's say you have a savings account that grows 5% per year, and that means they're going to calculate 5% of your savings and add it in as interest. And how much will you have in the account if the initial balance is $975 and it grows for 5 years? Okay, so the way we do that, this is going to be what's called compounded annually. So we're not going to worry about how this breaks down, you know, with monthly or daily or you know, hourly interest. It's going to be the initial amount times that rate of 5% plus 1 to the 5th power. Okay, so remember, this was the percentage growth rate. This is that 1 that keeps that essentially maintains that you're not doing anything with that initial amount, that carries forward. Like, for example, if it didn't grow, if it was exactly 0, it would be 1 to the 5th, which would be still 1, and so it wouldn't grow. You would always have 975. But since it grows, we're going to put the percentage growth rate, add it to that 1, and then take it to the 5th power, because it's 5 years, and then we get whatever this calculates out to be. We get $1,244.37. Okay, so in the first reading, in section 4.1, pages 222 to 226 deal with compounded growth. Like, it's a different question if you say if it compounds monthly with a 5% per year interest rate, what are you going to have? You get a different answer. And that's covered in these sections, 222 to 226. And I'm not going to cover them, and you're not responsible for them. But if you're interested in them, it's actually a pretty good section. Those 4 pages will tell you, how you take into account things like, quarterly or monthly compounding periods. So there is one section in there that talks about E, which I'm going to talk about next, that you should look at. But in terms of financial calculations, you're not going to get anything more complicated than this, okay? Because it's if you want to learn more about this kind of stuff, Math 3 is a good place to learn that. Okay, now oftentimes what you have is some notion that you have exponential growth, but you don't have the growth rate, you don't have the coefficients. What you have are 2 points, like 2 points in time. You make a measurement, you make another measurement, you have observed that it's not linear growth, so you probably have an idea that it's not really a straight line, it's some sort of curve or something like that. How do we fit it to an exponential function? Okay, so what you do is you take this thing and you stick in the points that you know. So remember, y is the dependent variable, which is 1 or 5, depending on which point you're looking at. And then the independent variable is the exponent. So you stick the -3 in the first one as the exponent, and then in the second one the exponent is 2. All right, now what you have to do is solve for a and b. And so this is more or less a general way to do this for any kind of functions when you have 2 different points and you have two things that you don't know, is that you solve for one of them. And notice that the a is just a coefficient. And so it's possible to solve for a in both of these. And so all I'm doing is rearranging this, dividing both sides by b to the -3 or b squared, and we get what a is. And now, since we have a, we can equate those two, right? We have, in the first equation, we get a equals b cubed. In the second equation, we get a equals 5b to the -2. And so we can make those two equal. And then all we do is solve for b. And so, since you're all experts at manipulating exponents now, we find that b equals the 5th root of 5. Okay, so from here then, we can solve a, because we can put the b back in either of the equations, and it looks like that first one's a little easier. A equals b cubed, so we just stick in a 5th root of 5 and cube that. And so our function then is a times b to the x. Now that probably looks pretty ugly, right? So you whip out your calculator and you get something that you can operate with, and that's what it turns out to be. But being the kind of guy I am, I will ask you to answer it like that. Okay, it looks uglier, but it's actually more exact. Okay? Any questions here?
I understand that the a equals
Okay.
All right. Now, you've heard me talk about E, and you see E here, and you either call that Euler's number or Napier's constant. Okay, so this was actually, E was first identified by a guy by the name of, I believe it was Bernoulli, who did a lot of work in fluid dynamics and things of that sort. Napier was the first one to really calculate it and do some things with it. But in terms of math kind of stature, Euler is, you know, if you ask a mathematician what are the 5 greatest mathematicians of all time, chances are he'll put Euler in that list. Euler did more with E than either Napier or Bernoulli, and so Euler actually used little e to represent the number, and so that has stuck. So when we use E, it's like using the symbol pi. You can use pi as any old Greek letter in any formula, but it's generally regarded as you know, the ratio of the diameter to the circumference, or the circumference to the diameter of a circle, 3.14159. E is always, not always, but it's frequently used as this constant. Now, E has about 20 different ways you can define it, and that's one of the amazing things about E. And so it oftentimes is called the natural base, too, because it comes up in nature quite a bit. Comes up in places that you wouldn't expect E to come up with. Now, you all know what a limit is, and so if you look at this limit, you don't know how to calculate this limit yet, at least by the tools that I taught you last semester. But if you think about that, 1 over x, as x goes to infinity, that becomes very small, right? And then you do something that's very close to 1 to the very, very large power, you really don't know where that ends up, right? You think, well, does it go to 1? You know, because 1 to the infinity power is 1, or, you know, but if you take a number slightly off of 1, 1 to some very large number is going to be a very large number. It turns out that that number settles out to exactly E. Now, another place that you can get E out of is that if you take this series, if you just look at factorials, if you do 1 over 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, and you do that infinitely long, you're going to get to E as well. Now, as far as I can tell, that very first equation and that second equation really have no obvious connection to each other, but they both turn out to be exactly E. And so, you know, I could go over a number of these. You don't have to memorize these per se, but what you should know is that E is going to be 2.718 is usually the way it's represented. And just like pi, it doesn't repeat nor does it terminate. So it's an irrational number. There's no ratio, no simple ratio that you can define that makes it a single number. Okay, so we're going to find that E, in higher math, E comes up all over the place, and you're going to be living with this thing. And it has some very distinct properties that are really kind of cool about E, at least a mathematician thinks they're cool, that e to the x, the derivative of e to the x is e to the x. You know, there's no other function that has that property where the derivative equals the function. Now, of course, if you have something more complicated than x, like e to the 2x, you have to use the chain rule to figure out what the derivative is. But you know, the derivative of e to any variable is just e to that variable. The other thing that's kind of remarkable is this. You know what I is? That's the square root of -1. We don't deal with complex numbers in this calculus or in algebra, so maybe you've seen this in high school, but e to the I pi equals -1. And you frequently see this as e to the I pi plus 1 equals 0, but it's the same thing. If you get into higher forms of math, like abstract algebra, this becomes a really, really important equation. And you don't have to know this, but to me, I first saw this as a senior in high school, and to me it was just surprising. Because think about it, e to the x, if x is a real number, is positive, right? Now I is an imaginary number, it's a square root of -1. Pi is a transcendental number, or it's a irrational number. So here we have two irrational numbers and an imaginary number making something very, very simple, -1. So it's just one of those kind of neat things I think that you discover in math, that you have these relationships that come out of seemingly nowhere. But there's a really, really elegant way to show this. But anyway, we won't go over it. I just wanted to highlight the fact that E shows up in a whole lot of different ways.
What is it called when the derivative of a function equals the function? Is there, I thought there was a word for that. Okay.
No, it's actually this is if we represent a function as you know, we can do this, right? And sometimes we just refer to the derivative like this, you know, the function and its derivative. If I rewrote that, we just get y equals y prime, and this is called a differential equation. And so we'll be dealing a little bit with differential equations in Math 28. And so if you take that next semester, it'll be your first non-Hans de Moore math classes at St. Mary. So that might be a good thing in itself.
Who do you think it would be?
I have no idea. Okay, so differential equations, a lot of physical modeling turns out to be differential equations. When you have a differential equation that looks something like this, usually it ends up to be a function that involves E. Okay, so that first property is the property that I want you to remember out of all this. So if there's two things on this chart that are important, first know approximately what this value is, and then also know this property. Okay, so let's look at exponential functions in general. And I drew some graphs here of several exponential functions. And if we start at the one in red at the bottom, f at x equals 1 to the x. Well, no matter what x is, including 0, it's always 1. So this is just a straight horizontal line. Now, if we have something like what I showed before, that 1.1 to the x, or in this case, this is going to be 2 to the x, we get this curve that increases, and it gets more and more steep as we go along. F at x to the 3 to the x is going to be even steeper. Now e to the x, which probably I should have put on this chart, but it's going to be somewhere in between these, probably closer to the 3 to the x. So e to the x would be some function that's in between those functions. So this is kind of its behavior when the base is a number larger than 1. When the base is smaller than 1, you get this curve that goes down. It starts really high, and then it goes, you know, down to close to 0 as you get to larger values of x. And so think about that. If you have 1/3 to the 10th power, that's 1/3 times 1/3 times 1/3 times 1/3 10 times, and so that's 1 over 3 to the 10th, which is a very small number. That's the reciprocal of 3 to the 10th. So there's certainly a symmetry between this 3 to the x and the 1/3 to the x. They're just rotated, they're symmetric about the y-axis. And so I also put in 1/2 to the x right there. And so these things tend to flatten out as the base gets smaller, gets closer to 1, and then when it gets less than 1, then it actually goes the other way where it's getting closer to 0 on the positive side, and when x is negative, then it gets larger. So this is generally what happens with exponential functions. And so we'll be dealing with these, of course, just the way they are. And then we also have this thing that, remember how we would translate different functions by either multiplying it by a positive or negative or some coefficient, or adding a number to x or to the function. And we do the same thing with exponentials. And so to remind you how that goes, remember if we have this function g to the x, and then we say f at x is any function, that h here moves at h units to the left, and then k moves at k units up, although I probably should make that a positive k. How's that? Remember that? And then you stretch and shrink things but with a. So with a curve like an exponential curve, it's kind of hard to draw compared to a polynomial curve because they all kind of look the same. It's a question of where they go through. So it's perhaps easy to decide what's happening with these, but to actually graph it, you probably need to put a few points on there. So let's put this with an exponential function. So if my exponential function is b to the x, I can move it around by either adding to the exponent or adding to the function. Whoops. Sorry about that. So you can see here that when you have something in the exponent, this is going to move it back and forth, and then this one is going to move it up and down. And then, of course, the coefficient just says what the starting point is. That's where it goes through the x-axis when x is 0.
So you can just magically use it the same way, even though it's in the exponent area?
It is exactly the same thing that we talked about. There was nothing that made that depend on doing anything other than adding the h directly to the x before you do anything to it, and then when you're all said and done, you add the k. Then it's going to be moving it left and right, up and down. Okay, and then the a, of course, the sign of it can flip it upside down, so they're always negative and all that kind of stuff. So just as an example, let's say I have f at x equals 2 to the x, and then my translated one, if I multiply it by -3 and then I take it to the x minus 2 plus 1, I get something that looks very similar. And what I said earlier about sometimes it's hard to graph this, you're probably best off choosing a couple really easy points to draw the curve through. So if you're just doing a regular one, you know that as x increases you go off, or as x goes to -infinity, that the function goes to 0. So you can see that the green line, it tails off here and it gets closer and closer to 0, doesn't actually ever reach 0. And then two values that we know, f at 0 is going to be 2 to the 0, which means that that's 1. So it's going to cross the y-axis at 1. F at 2 is an easy calculation. That's 2 squared, which makes it 4. So I just have this point that I can put through here. So if I know then that it tails off to close to 0, where it intercepts, and then one other point just to give me some indication of how steep it is, that's probably the easiest way to graph this. Just put two explicit points, and then where does it go as you go off to infinity. So when we look at this -3 times 2 to the x minus 2 plus 1, let's say we didn't see the graph, how would you graph something like that? Well, the negative flips it upside down, the 1 moves it up and down, the -2 moves it back and forth somehow. Just stick in some numbers. As you go to infinity, okay, this first part goes to 0, right? Because if this is really, really, really huge negative, you get a very, very small number, and so the only thing that matters then is this 1, and so we have this horizontal asymptote as 1. And just so you understand that when you take an exponent to a negative number, a very large negative number, you're very close to 0. So we expect an asymptote at 1. And then put in a couple easy numbers. X is 0 and x is 2 give you two really easy calculations, and you can pop those two down. And so there's an easy way to graph it. So unlike a parabola where you didn't really have to worry too much, you just kind of figured out its vertex, and you could kind of massage its shape a little bit by putting 1 or 2 points. With an exponential curve, usually you can figure out its intercept pretty easily just by making x equals 0, and then you make the exponent 0 by taking, in this case it's 2, because 2 minus 2 is 0. You actually have two very straightforward calculations that you can get 2 points pretty directly. So then it's the only complicated part is to figure out where does it go asymptotically as that exponent gets really, really negative. Or in the case of the bases being like 1/2, then when the exponent gets very, very large on the positive side. So it takes a little feel. You'll have some exercises on this in in the homework. Okay? I'm going to go run down and get the roll, and then I'll take roll. Okay, so hang on just a second.